Good morning, student. Today I will explain about Laplace equation in three dimensions. Okay, see equation in three dimensions. Okay, therefore, see in this case the value of v in this case the value of v at point r is the average is the is the is the average value of v over a spherical surface or a spherical surface of radius say capital R centered at small r. Okay, and therefore we can write v of r is equal to 1 upon 4 pi r square, where capital R is radius of the sphere, close integration of v into dA, where dA is surface element or sphere, close integration over sphere, and this is your equation number 1. V of r is equal to 1 upon 4 pi r square, or you can write average potential V of r centered at small r is equal to 1 upon 4 pi r square into integration of close integration of VTA, and dA is surface element. Okay, this is your point number 1 for properties of Laplace equation in 3 dimension. Okay, second point is we we can have no important word, no local maxima, or minima. The extreme values of v, the extreme values of v must occur at the boundaries. Must occur at the boundaries. Okay. See, these are the properties of Laplace equation in 3-dimension case. Laplace equation in 3D. Okay. What are the main points? The value of v at point smaller is the average value. Is the average important word, or a spherical surface of radius. Capital R is the radius of sphere and centered at small r, where v of r average potential can be written as 1 upon 4 pi r square closed integration of VdA up over sphere, and we can have no local maxima as well as minima, and the extreme values of v must occur at the boundaries. These are the two basic properties of Laplace equation in three-dimensional case. And in this case, what are the main points? In point number one, value of v at point what? R, small r, is the average value. This is the important word, average value, or close integration of V into dA. See, average potential is equal to 1 upon 4 pi r square. R is the radius of sphere into integration of close integration. Which type of integration? Close integration. V potential into surface element dA, and where surface element dA is above is r square into sine theta d theta into d phi. That is for spherical symmetry. And point number two, in point number two, uh, main points of we can have no local maxima. This is the important word. Low, no local maxima as well as minima. Okay, but it has extreme values at the boundaries. Extreme values at the boundaries. These are the two important properties of Laplace equation. Okay, then we will find the average value, average potential value for sphere of radius capital R, or you can show that average potential is equal to 1 upon 4 pi epsilon 0 q by z. We will show that. Okay, see, next point is these are the properties of Laplace equation in three-dimensional case. And then next we will find out the average potential for sphere of radius capital R. See the next point. Yes, next point is see, show that average potential V average is equal to 1 upon 4 pi epsilon 0 into q by z. Okay, our aim is to derive an expression for average potential for sphere 1 upon 4 pi epsilon 0 q upon z. Okay, and for this case we will assume one sphere with radius capital R. See the diagram. For that, first I will draw the diagram. See, I will take one sphere. Okay, consider this is a sphere of radius capital R. Okay, in three-dimension case, I will show first This is a sphere in 3-dimensional. Suppose this is the center. Okay. Then this is your x-axis. Y-axis. Then this is z-axis. Okay. And origin, say O. Origin means intersection of x-axis, y-axis, and z-axis. Okay. Then this is radius, capital R. We can write here capital R is the radius of the sphere. Then we will assume a charge particle Q along z-axis. Okay, along z-axis. Suppose this is a charge particle denoted by Q along z-axis. Okay, and then we will take one small spherical element, surface element, say okay, this is a surface element with area, say with area dA. Okay, I will take this is your surface element with area dA, and which is on the surface of sphere of radius small capital R. Okay, I will use different color dA. Okay, surface element with area dA. Then I will join the center of this dA with origin of the sphere O. Therefore, see. Okay, again this is your capital R, the distance between surface element and origin, that is your capital R, capital R. Okay, then I will join the surface element with charge particle Q like this. Say this is your small r. Okay, thus see, in this case single point charge, that is Q, is along z-axis. Q is along z-axis. dA is the surface element. The distance between origin of the sphere and surface element is capital R, that is the radius of the sphere. This sphere with radius capital R is in 3-dimensional case, 3-dimensional system, X, Y, and Z. Q is the charge particle along z-axis. The distance between surface element and charge particle is smaller. Our aim is to show that average potential for sphere is equal to 1 upon 4 pi epsilon 0 Q upon Z. Okay. Therefore, we can write in this case a single point charge, that is Q, located outside the sphere. Here I will write a single single point charge, that is q, single point charge q, located outside the sphere. Outside the sphere. And center of the sphere located at the origin. Located at the origin 0, 0, 0. Okay. Origin means intersection of x-axis, y-axis, and z-axis. Okay. And from this, uh, in this case, q lies on the z-axis. Therefore, here I'll write q lies on the z-axis, and therefore the potential at a point on the surface, and therefore the potential at a point on the surface can be written as I will shift this part just away, upper side, can be written as equation number 1, like v equal to 1 upon 4 pi epsilon 0 q upon r, equation number 1. Okay, equation number 1. And therefore from this geometry we can write using cosine law we can write r square is equal to z square plus capital R square minus 2 times zr cos theta based on cosine law. Okay. Again, we know that dA is your surface element, which is equal to r square sine theta d theta and d phi. Say equation number 3. Okay. We have here equation number 1 is v equal to 1 upon 4 pi epsilon 0 q by r. From this geometry, we can write based on cosine law, r square is equal to z square plus capital R square minus 2zr cos theta, and d is which is your surface element, spherical surface element, capital R square sine theta d phi, where capital R is radius of the sphere. Okay, and therefore from the knowledge of or based on the properties of Laplace equation in 3-dimension case, V average potential is given by V R. V average is equal to, basic equation for average potential is V average is equal to I can write V average is equal to 1 upon 4 pi r square close integration of v into dA. This is your basic equation. Say suppose equation number 4. Equation number 4 is a basic property of Laplace equation in three-dimensional case. Okay, and therefore we have v, that is your equation number 1. We have dA, that is your equation number 3. And therefore putting the 1 and 3 in equation 4, we can write, see, here I'll write, putting equation 1 and 3 in equation 4, we get just put the term of v and v and dA in equation 4. Therefore we can write equation 4 can be written as v average, I will write only vg, is equal to 1 upon 4 pi r square integration of v. What is the v? V is your 1 upon 4 pi epsilon 0 into q by r into r square sine theta d theta into d phi. Okay, again in this case small r is distance between surface element and charge particle q. Okay, and again from cosine law r square is equal to z square plus r square minus 2 times z into r cos theta. And from this equation 2 we can write from equation 2 we can write r equal to root of z square plus r square minus 2 zr cos theta. Okay, and therefore see, this is your equation. I'll write here equation number, next equation number is suppose uh, 5. Okay, from equation 2 implies that small r is equal to, we can write here z square plus r square minus 2 zr cos theta raised to half, okay, and therefore putting the value of small r in equation 5, we can write, I will shift this, yes, we can write rewriting above equation 5, we can write here rearranging this equation. In this case q is constant, take outside, 4 pi into 4 pi, that is 4 pi bracket square into r square into epsilon 0 integration of r square sine theta d theta d phi whole divided by z square plus r square minus 2zr cos theta raised to half. Okay, yes, this is the rewriting equation number 5, we can write like this. Okay, and therefore using substitution method we can find this integral part, that is your RHS. Okay, and therefore using substitution method we can find out the denominator term, and again from this again here in this we can using see here r square is r square, and this is again your r square term, we can cancel r square and r square. Okay, and therefore we can write using substitution method. I will take denominator, I will assume denominator term equal to small t. Therefore, see, that can be written as, yes, okay, see, here I will cancel r square and r square term. Okay, and therefore we can write q upon 4 pi square epsilon 0 into bracket sine theta d theta upon z square plus r square minus 2zr cos theta raised to half, and again integration of d phi from 0 to 2 pi, and here 0 to pi. Okay, and therefore here I will make two parts. Okay, see, integration of d phi from 0 to 2 pi can be written as phi from 0 to 2 pi. Okay, that is equal to 2 pi minus 0, that is equal to 2 pi. Means for this case we can write only 2 pi. Then next point is sine theta d theta upon z square plus r square minus 2zr cos theta. Okay, in this case, in this integral sign, integral term, a denominator is z square plus r square minus 2zr cos theta. Therefore, here we will assume small t is equal to z square plus r square minus 2zr cos theta. Okay, and therefore taking derivative with respect to theta, that is dt by d theta equal to d by d theta of z square plus r square minus 2 times zr cos theta is equal to d by d theta of z square plus d by d theta of r square minus d by d theta of 2zr cos theta. Okay, and for this case uh, I will use different color. For this case, see, derivative of z square with respect to theta is always 0. Again derivative of r square with respect to theta, again 0. Okay, and therefore for this case I can write this term, and d by d theta of r square should be equal to 0. Therefore I will write dt upon d theta equal to 0 plus 0. From this we can take minus is the sign, 2zr constant, take outside, and derivative of cos theta is minus sine theta. Okay, and therefore we can write dt by d theta. I will shift this. We can write 1 minute. Yes, or okay. I will write. We can write dt upon d theta is equal to 2 zr sine theta. Okay, and therefore rearranging this term, we can write dt upon 2 zr is equal to sine theta d theta. Okay, and therefore this can be written as q upon 4 pi square into epsilon 0. Instead of sine theta d theta, I can write dt upon 2 zr whole divided by t raised to half integration 0 to pi. And for this case, integration of d phi from 0 to 2 pi is your 2 pi. Okay, and therefore again we can write q upon 4 pi square epsilon 0. In this case 2zr is a constant. I can write 2zr into 2 pi is again constant, take outside, and we can write 0 to pi t raised to minus half dt, t raised to minus half dt. Okay, and therefore again we can write here. I will write from this. Yes, this is your okay. Therefore from this here q upon 4 square 16 pi square epsilon 0 into 2 times zr. Here we can use bracket into 2 pi. Okay, again t is z square plus r square minus 2zr cos theta. Okay, and for this we can write t raised to minus half integration of t raised to minus half dt is t raised to minus half plus 1 upon minus half plus 1. Okay, from 0 to pi, and then we can discard, we can cancel some constant term. Okay, see, yes, therefore here we can write q upon 16 pi square epsilon 0 1 upon 2 zr into 2 pi t raised to minus half plus 1 is t raised to half upon half from 0 to pi. Okay, here we can cancel 2 get cancelled, pi pi. Okay, therefore rewriting this equation can be written as q upon 16 pi epsilon 0 into 1 upon zr. This can be written as z square plus r square minus 2 zr cos theta from 0 to pi. Okay, this is your V average, and then we can write we can write we can use next new page. Okay, see, previous page is V average equal to q upon epsilon 0 into 1 upon zr into bracket z square minus 2 zr cos theta from 0 to pi. Therefore, rewriting same equation on new page like this, I will use new page. Okay, see, rewriting previous equation, that is V average is equal to q upon 16 pi epsilon 0 1 upon zr into z square plus r square minus 2 zr cos theta from 0 to pi. Okay, therefore see, putting the upper limit and lower limit, upper limit is pi and lower limit is 0. Therefore q upon 16 pi epsilon 0 into 1 upon zr. Okay, and therefore we can write here we can write putting upper limit z square plus r square this is raised to half. एक minute. Next point is minus 2 z cos of pi raised to what, half, minus z square plus r square 2zr cos of 0 raised to half. Therefore, this is your q upon 16 pi epsilon 0 1 upon zr z square plus r square minus 2zr cos of pi is minus 1 raised to half minus z square plus r square minus 2zr cos of 0 is 1. Okay, 1 raised to half, bracket complete. Okay, and therefore q upon 16 pi epsilon 0 into 1 upon zr, okay, into this can be written as z plus z square plus r square plus 2zr raised to half minus z square plus r square minus 2zr raised to half. Okay, like this. And therefore we can write, see, for this we can write z plus r bracket square. For this we can write z minus r bracket square. Okay, and therefore we can write like this. From this average potential, 1 minute, upon zr into z plus r bracket square raised to half minus z minus r bracket square raised to half. Okay, and therefore here q upon 16 pi epsilon 0 into 1 upon zr in this square get cancelled, square get cancelled, 2 into half, again 2 into half, that is z plus r minus z minus r. Okay, then see, before that I will show the previous one step. See, in this case 2 pi, and this is your half, that becomes, this half becomes 2 times of, this is your half, this becomes 2 times 2 into this. Okay, and therefore your LHS is your twice of V average. Okay, therefore see, this is your twice of V, twice of V. Next is and thus we can write Q upon 16 pi epsilon 0 into 1 upon Z R into bracket Z plus R minus Z plus R. Okay, therefore Z get cancelled and Q upon 16 pi epsilon 0 into 1 upon ZR into bracket R plus R is 2R. R plus R is 2R, and thus we can write Q upon 16 pi epsilon 0 into 2 by Z. Okay, 2 by Z, and therefore R get cancelled, 2 by Z. This is your V potential, V average. Okay, that can be written as Q upon 8 pi epsilon 0 into 1 upon Z. Okay, again uh, this is your half of average potential. See, this is your 1 by 2. Okay, and therefore we can write 1 by 2 of, that is half of V average. V potential can be written as um, this is your half. Okay, half. That's half V average. That's half V average is equal to Q upon 8 pi epsilon 0 into 1 upon Z. And from this, average potential can be written as 2 times of 1 upon 8 pi epsilon 0 into Q upon Z, that is equal to 1 upon 4 pi epsilon 0 into Q upon Z. This is final equation. Okay, thus we can say that V average, that is average potential, uh, is we can conclude that for any collection of charges outside the sphere, their average potential over the sphere is equal to the net potential they produce at the center. And thus we can here write their average potential, this we can write here, their average potential thus their average potential of the sphere is equal to the is equal to the net potential they produce at they produce at the center. Okay, this is about the average potential of sphere, where in this case charge particle is along the z-axis. Okay, this is the derivation of V average. That is the one important parameter of Laplace equation in 3-dimension case. Thus V average equal to 1 upon 4 pi epsilon 0 q by z. Okay. Yes, any doubt up to this level? Thank you so much.